part 3 of the third organ number theory day.
Well, thanks for coming back. I think it might be a little better if I were better at drama and I could pretend to be a completely different person. But since I'm not, at least I'll talk about something completely different in this hour. And this is, I'd like to thank the organizers again. And so this is a project in Galois theory and Galois cohomology. So I'd like to just give some overview of some of the big open problems in the area that are sort of motivating this project. Even though they're not directly related to this project itself, there's some really important questions that you've probably heard of before about Galois extensions and about rational points. But then along the way, we need a lot of results about Galois extensions of number fields, and so that will show up. And then a lot of this talk is about Galois cohomology for Fremont curves, and so that will be the main topic. And all of this work is joint work with Davis and Wickelgren. Also, Vesna Stojanowska was involved with some of the earlier parts of the project, and Özlem is involved with some of the later parts of the project. And so I'll try to be clear about who helped with what along the way. Okay, so this is the abstract. So in general, if you have a curve defined over a number field, then we've got the absolute Galois group of that curve, and it acts on everything associated with that curve. In particular, it acts on the fundamental group and on the homology groups and on the Jacobian. And so this talk is about looking at that action when X is the Fermat curve. And Anderson was the one who first started proving theorems about this action on certain homology groups of the curve, with the coefficients being taken mod n. And so the main goal of what we've been doing is to try to make Anderson's action really explicit, in that it could actually be put on a computer and calculated, and that certain invariants of that action could be computed. And so that's what we've done. Along the way, there's sort of lots of different coefficient rings that are sort of complicated, that involve understanding different cohomology groups and maps between cohomology groups. And so we've spent a lot of time trying to understand those maps, and actually calculating things involves some fun combinatorics. Okay, so let me start by just telling you about some Galois extensions of number fields that are ramified only over one prime. So the prime p is going to be an odd prime, and we're going to take zeta to be a pth root of unity, and we'll look at the cyclotomic field. So this is a field that's degree p minus 1 over q, and it's a Galois extension of q with group the roots of unity in z mod p. And it's ramified only over the prime p. And if you look at the factorization of p, it factors as 1 minus this root of unity to the p minus 1. So the field that's going to show up a lot in this talk is this field L. And this field L is the splitting field of this polynomial, 1 minus x to the p raised to the p. And in order to get a field that contains all the roots of this polynomial, you in particular need to have a pth root of unity. So this cyclotomic field K is contained in L. And there are lots of other things you can show about this field L. It turns out that this field L is ramified only over the prime 1 minus zeta. And in fact, it's generated by the pth roots of 1 minus zeta to the powers I, where I goes from 1 to p minus 1. And there's a relationship between this cyclotomic unit and the one for as you change the exponent to negative I. And so that means that, in fact, you can generate this field L using just the p squared root of unity and the pth roots of 1 minus zeta to the I, as I ranges from 1 to p minus 1 over 2. So what that means is that the way we've generated this field L is by taking pth roots of a bunch of things in OK. And as a result, the Galois group of this field extension is an elementary abelian p group. It's just isomorphic to z mod p to a certain power. And it turns out that, well, from this description of L, we can see that that power has to be less than or equal to this number r plus 1. And it turns out that the rank is exactly equal to r plus 1 if and only if Van der Waals conjecture is true for the prime p. So, this here is probably one of the most unusual formulations of Van der Waals conjecture. So let's just remember what Van der Waals conjecture says. This was first conjectured by Kummer in 1849. And the idea is that you look at the cyclotomic field, and then you intersect it with the real numbers to get the real cyclotomic field. And you look at the class group of that, of fractional ideals modulo principal fractional ideals. And that's a finite group whose size is the class number h plus. And Van der Waals conjecture is that the prime p does not divide that class number. And this has been checked for all primes less than 163 million, and it's just true by definition for all regular primes. Okay, so that was sort of a mouthful. Any questions about this field here? So I think what's most interesting to me about this field is that somehow with one fairly straightforward polynomial, we can then find an extension of K, whose Galois group is an elementary abelian P group, and it's ramified just over the prime P, and somehow understanding the size of that group is equivalent to proving Van der Waals conjecture. Any questions so far?
So L over Q is also only ramified at one?
At one prime, yeah. Okay, so it's sometimes more interesting to look at non-abelian extensions. And so here's a non-abelian group for which you can construct Galois extensions. So we're going to look at the Heisenberg group. The way you make the Heisenberg group is you look at upper triangular 3x3 matrices. You take their coefficients to be in Z mod P, but put 1s on the diagonal. So that's a group of size p cubed. And inside it is the normal subgroup where the only non-zero entry off the diagonal is the upper right entry. And that's actually in the center of HP. And so from that, you can make a short exact sequence with this group of order p cubed, this subgroup of order p, and the quotient is a cyclic group of order p squared. And this extension, it turns out, is classified by a certain cup product in H2, a group cohomology. And so there's this really nice thesis of Ramyar Sharifi. And so this particular result was known earlier, but he generalized it into some more arbitrary groups and also for twisted Heisenberg groups. And the question is, how can you make Heisenberg extensions of a number field? And so one way of doing that is you take a field and you adjoin a pth root of two things. So let's adjoin a pth root of A and a pth root of B. And so usually that will have Galois group Z mod P squared. So let's just assume that A and B are independent. So you get a Z mod P squared Galois extension F of K. And the question is, when is there a Heisenberg extension which dominates that? And it turns out the way of figuring that out is by evaluating certain Kummer symbols, which I realized are not defined until slide 20, so just take them for granted for a little while. But you sort of look at certain Kummer symbols, which are elements of H1, and take their cup product and see whether that's 0 in H2. So it turns out that we can make that using the extensions that we had before, we can make Heisenberg extensions. And the way is to take A to be the pth root of unity to some power, and B to be 1 minus that pth root of unity to the same power. So these fields here are then subfields of the field L we talked about before. There's something called the Steinberg relation, which says that in this case, the cup product is 0. And so it's possible to make a field extension dominating this one, whose Galois group is the Heisenberg group. So from these elementary abelian P group extensions, we can dominate them by Heisenberg extensions. And it turns out that you can do this really explicitly. The way you do it is by taking a pth root of this element. And this element was chosen so that we can take the Galois actions of multiplying these things by pth roots of unity, and we can extend those and get the Heisenberg group acting on this field. And so here's explicitly how this Galois action should act on this element. It takes it to this. So really concretely, when P is 3, then you would join a cube root of this element here, where omega, I should have said, is a ninth root of unity. So the idea here, and there's a whole community of people working on these things, is that for different P groups, it would be nice to be able to construct Galois extensions of number fields that have those Galois groups and are ramified only over P, and these are some examples of how to do that. Okay, so let's just take a major step back and say, what's the major open problem in this area that's motivating all this research? And it's the inverse Galois problem. And so one way of saying the inverse Galois problem is that if you pick a field, for instance, the field Q, a number field, and if you take a finite group G, one expects that there's a Galois field extension, L over Q, having that Galois group. So the conjecture has been made that this is true. And in fact, a much more general statement is true, that you should be able to pick any field that you like here as a number field, and be able to pick any finite group and generate this Galois field extension here. So what's some of the evidence for this conjecture? So Shafarevich proved that it's true if G is solvable, in particular for these P groups. And so the field community's been working on more refined questions like where are these extensions ramified, and can you get them to be ramified only over finitely many primes. This conjecture is also true for all finite sporadic simple groups except the Mathieu group, M23. It's also true for many matrix group. And so more generally, what we want to do is to pick a number field K and look at the absolute Galois group GK, which is the inverse limit of the system of all the Galois groups of Galois extensions of K. And so the inverse Galois problem asks whether this group, this unknown profinite group, whether it surjects onto every finite group G. So sort of the main, sort of in the background, the main thing motivating a lot of research directions is to understand this group GK, this absolute Galois group, because we don't know basic facts about it, such as what its finite quotients are. Okay, so Grothendieck had a different perspective on trying to understand this absolute Galois group. So his perspective was, rather than trying to build field extensions that have a certain Galois group, we should instead try to understand this group by how it acts on geometric objects. And in particular, he looked at geometric objects like curves. So there's a lot of research about fundamental groups of moduli spaces of curves of genus G with n-marked points, and sort of certain important levels of this tower, and the Teichmuller tower involve cases where the genus is just 0 or 1 and the number of points is small. But there was a big theorem of Bailey which really changed the direction of Grothendieck's program. And what Bailey proved is that if you take an algebraic curve X that's defined over a number field, then it should admit a covering of the projective line ramified only at 3 points. And so every algebraic curve defined over a number field can be characterized as has a covering of P1 ramified only at 3.01 infinity. And so if you've seen any of these talks, for example, about Bailey maps or descent d'enfant, this is all based on trying to understand the absolute Galois group of Q in terms of these coverings. And why is that? It's because this absolute Galois group has a faithful action then on the algebraic fundamental group of P1 minus 3 points, which is a free profinite group on 2 generators. And so it is, in theory, possible to give a purely algebraic description of this absolute Galois group, not in terms of its finite quotients and how they fit together, but just in terms of how it acts on a free profinite group on 2 generators. And so Deligne and Drinfeld and Ihara spent a lot of time on this, and they showed that the elements of GQ had to satisfy certain relationships, and based on that, they defined the Grothendieck-Teichmuller group, and it's still an open question whether these groups are the same or not. So that's somehow a motivation about why it would be worthwhile to try to understand the action of the absolute Galois group of number fields on certain geometric objects. So in this talk, we're going to be talking about the Fremont curves. And so for a number n greater than or equal to 3, the Fremont curve is just the curve x to the n plus y to the n equals z to the n. It has affine equation x to the n plus y to the n equals 1. And Fermat's last theorem says that if you have a rational point on this curve, then one of the coordinates has to be 0. So these Fremont curves turn out to be abelian covers of the projective line minus 3 points. And more generally, any abelian cover of the projective line minus 3 points is dominated by a product of Fremont curves. So for instance, these cyclic covers can be dominated by certain Fremont curves. You can also think of the Fremont curve as a quotient of the upper half plane by a subgroup of certain congruent subgroups. So these,
What do you mean by dominated?
like there's a map from the Fermat curve to this curve. Yeah. Yeah. So these are the Fermat curves. And so lots is known about the Fermat curves. So for instance, the genus of the Fermat curve is n minus 1 times n minus 2 over 2. And there are certain cusps on the Fermat curve, which are the points where one of the coordinates is 0. So for instance, we have this z is the set of n points where the z coordinate is 0. And we have an affine subset of the Fermat curve where you get rid of those points. You could also look at the points capital Y where either x or y equals 0. And so what do these points in Y look like? They look like x being a nth root of unity to some power 0, or 0 and nth root of unity to some power. And so there are 2n points like that. So it turns out that a lot of the homology of the Fermat curves can be described just by thinking about one path. And the path that we're going to focus on is the path that starts at this point 0, 1, and it ends at this point 1, 0, and it takes t to the nth root of t, the nth root of 1 minus t. So that's a path. That's a path in the Fermat curve. And from that path, or associated to the Fermat curve, we can then look at homology groups. So these are étale homology groups that have coefficients in z mod n. And so the one that is most familiar is the homology of the projective curve x, and that has dimension 2g. A slightly bigger homology group is h1 of u, which has dimension n minus 1 squared. So one way of thinking about this homology group h1 of x is it's the abelianization of the étale fundamental group of x. But one trouble with both of these dimensions here is that they're kind of awkward in terms of n. Like they're not a clean formula in terms of n. And why would you want sort of a nice formula in terms of n? Well, this curve has an action of some automorphisms. You can act on this curve by taking x to an nth root of unity times x, or taking y to an nth root of unity times y. So there are n squared automorphisms of this curve, and those automorphisms, they fix this affine curve. They actually fix the set of points z where z equals 0. They fix the set of points y where xy equals 0. So we have some really nice geometric automorphisms, and there are n squared of those automorphisms. But these dimensions are not a nice formula in terms of n. And so it turns out that if you instead look at the relative homology, and naively speaking, what this means is that instead of looking at loops, we take paths whose beginning and end point is in this set, in set Y. So we're going to take loops in U whose beginning and end point is in Y, and then consider their classes in this relative homology. And this relative homology has dimension exactly n squared. And so that's a really nice clean formula in terms of n, and its dimension exactly equals the number of geometric automorphisms we just talked about. So the goal is for this k being the cyclotomic field, which is not quite as great as q, because we had to add a root of unity. But notice that all the cusps are defined over this field. So we need to go up to the cyclotomic field. And if we look at the absolute Galois group of this cyclotomic field, a goal would be to determine the action of this absolute Galois group on these homology groups. And the one that's going to be easiest is this one, because it has an easier dimension. So we've got these automorphisms acting by taking x to an nth root of unity times x and y to an nth root of unity times y. And that group acts on that curve. So we can take a group ring for that group with coefficients in z mod n. And that group ring is going to act on the Jacobian and all other homology and cohomology groups for this curve. And so because these dimensions are equal, there's some hope for this theorem to be true. So what Anderson proved is that this relative homology with coefficients in z mod n is a free module for this group ring with rank 1, with this generator being that one chosen path. So let's think about what that means. That means that if you want to understand the action of the absolute Galois group on this relative homology, you just need to understand how it acts on that, how automorphisms of GQ act on this path. Because everything else in here is a linear combination of these automorphisms acting on that path. And let me just say that Oslam has generalized Anderson's results, but taking the coefficients from z mod n and replacing them with integral coefficients. Okay, so we have a basis for this homology group, and the way you find that basis is you take our starting path, which is the easiest possible path, and then you act by these automorphisms, and those give you other simplices in this homology that generate it. So the goal then is to determine the action of this absolute Galois group on this relative homology by finding the action on that one path. And so Anderson proved another big result, that if you take n to be a prime number, then the action of this absolute Galois group on this homology factors through that field L. Remember, L was that elementary abelian p-group extension of the cyclotomic field from the beginning of the talk. So L is the splitting field of this polynomial. So this is a really powerful theorem. One drawback is that the coefficients are all taken mod p, but it tells us that if you want to understand the action of this unknown profinite group, you don't have to worry about that unknown profinite group. You can just worry about the automorphisms of this field L and how they act on this path. So this theorem provides a major simplification, because rather than dealing with unknown profinite groups, we can deal with just a very finite extension of number fields that acts on the homology. And so in some earlier work, what we did was we took this theorem of Anderson and some other things that he did, and we tried to make this action really concrete. And by concrete, we mean not just like a concrete equation, but actually like something you could put on a computer. And so we determined an explicit formula for the action of Galois automorphisms of L over K on this relative homology for all odd prime P satisfying Van der Waals conjecture. And if there's time, I'll say a little bit more about this at the end. So let's think a little bit more about this homology group. Where did it come from? Well, we have a tall fundamental group of X. So this classifies all unramified covers of X, the whole inverse system of all the unramified covers of X. And that group is a non-abelian group. And if you look at its commutator and take this fundamental group and mod out by a commutator, you get this homology that we've been talking about. So this homology is the first quotient in the lower central series of the fundamental group. And it characterizes abelian unramified covers of the Fremont curve. But if you want to understand non-abelian unramified covers of the Fremont curve, then you have to go further in the lower central series. So you could take the commutator of the commutator with the fundamental group and make the next quotient, pi 2 mod pi 3, in the lower central series. So understanding this quotient tells you information about two nilpotent extensions of X. So this group, which is also an abelian group, kind of gives information about the whole system of covers, unramified covers of X. And so I'll say a little bit more about why we were motivated to look at this group a little bit later on. So our most recent result is, if you look at the Fermat curve of exponent n, what we do is to characterize this second quotient in the lower central series with coefficients in Z mod n as a GK module where GK is the absolute Galois group. So for any odd prime satisfying Van der Waals conjecture, we can actually determine how elements of the absolute Galois group act on this second quotient in the homology, in the lower central series. Okay, so let's try to make this really concrete. So let's take P to be 5. So K is the degree 4 cyclotomic field. And here's the Fremont curve. It has genus 6. And so it turns out then that the H1 of X has dimension 12, and GK acts on that. And so one thing you can tell from these explicit formulas is you can compute what's the subspace of this, which is invariant under GK. And it turns out that subspace has dimension 8. And so that is a sort of an example of our first theorem. And then in this situation, for the second theorem, we would look at this second quotient in the lower central series. It turns out its dimension is 65. And you can look then at the GK invariant subspace of this second quotient, and it turns out it has dimension 32. And so these calculations were all done on magma. And you can also, other kinds of things that you can figure out are which power of an automorphism minus 1 trivializes this homology or this second quotient in the lower central series. So that's somehow like saying how many iterates of an automorphism do you need to take before you act like the identity? And so just to reiterate this, so the kind of the amazing thing somehow is that these give the full action of the full absolute Galois group. But the drawback is that the coefficients are always taken mod p in all these calculations. Yeah.
So for that, the Galois invariant subspace has
Yeah.
dimension 8. Do you know like a formula when you change that? I guess the exponent pi, if you just take arbitrary.
Yeah, I mean, so in theory, we could, if you have your favorite prime, we could compute this for any prime. But the computations are pretty long, so we've actually only done them out through 7. So through the prime 7.
So do you know in this case that the dimension will be something like?
Like a consistent formula.
Yeah.
We have sort of upper. I forget if it's an upper or lower bound, but we have a. I would say we don't really know exactly what that would be for an arbitrary prime p. Yeah. Yeah. Any other questions? So I just this stuff. It's not really number theory, but I thought it was really kind of neat. The idea is that this second quotient is somehow not too hard to understand. It just comes out as a wedge product of the homology with the homology modulo one thing. And so really, if you want to understand this second quotient in the lower central series, this is all algebraic, understanding this part. So really, all you have to do is figure out what this one thing is that gets trivialized. And so why is only one thing trivialized? There's a map from h2 of x to h1x wedge h1 of x, which is dual to the cut product. And so it's the image of that map which goes to 0. So how do we understand what that one thing, delta bar, is? Well, this fundamental group is an affine curve of genus G with n punctures. And so the fundamental group has a presentation that looks like this, generated by AI, BI, and CJ, where I goes from 1 to G and J goes from 1 to N, and modulo this relation. This is the relation that's trivial in the fundamental group. And it turns out that this delta bar is the sum, as I goes from 1 to G, of AI wedge BI. So in order to figure out what this thing is, somehow what we need to do is to find loops. These CJ, what are they? They're loops that go around the punctures. Take the product of them, write that as a product of commutators, and then use those commutators to find this thing here. So we first did this for n equals 3 and tried to do it really explicitly. So it turns out that if you want to make loops that go around, there are 3 points at infinity. And if you want to make loops that go around those points, here's one way of doing it. You go from 0, 1 to 1, 0. You just sort of trace out a whole bunch of these paths, which we gave names for before. And here's a loop going around another point at infinity, and here's a loop going around another point at infinity. So these are 3 loops, and they turn out to be these 3. We have to take the product of these 3 things, and then express them as a product of commutators where those things are at h1 of u, and then find this. So this last step is going to be easy, but taking a whole series of things and finding them as a product of commutators, that is not so easy to figure out how to do that in general. Like, we don't know what the AI and BI are, and as a product of commutators, how do you get this whole mess to be written as a product of, in this case, this is a genus 1 curve. So this is just the product of one commutator. And so how can we figure out how to do that and then generalize to an arbitrary m? So where did those loops Ci come from? Well, this Fremont curve, we can think of it as a cyclic cover of the projective line with equation y to the n equals 1 minus x to the n. So by just forgetting the value of y, this gives a z mod n Galois cover of the projective line. And where is it branched? Well, it's branched where y equals 0. So that's where x is an nth root of unity. And so if you take if you imagine the projective line and get rid of infinity, so that's just a complex plane, and then you imagine these points where somehow all three branches of this cover come together over those points, then if you delete this shape here and delete the portion of x that lies above that star shape, then that's a way of taking this cover x and making it a three disjoint copies of things that map down to this subset of the complex plane. So after you remove these slits and their preimages, we have an unramified cover of a subset of C, and there's one of the cusps in Z is on each sheet of this cover. And so it turned out that these loops Ci, which we have formulas for them for general n, are loops that start at this base point and go around these points of Z. So what do those loops end up looking like? In general, each of them, there are n of them, and each of them is the composition of two n squared paths. And when you take the composition of those n loops, each of the edges, Eij and Eij inverse, from the relative homology shows up exactly once. So in other words, when we take the product of all of these things, we get this huge product of these paths, Eij and Eij inverse, but each one shows up exactly once. And somehow the idea is that we want to figure out how to write that as a product of commutators, and then how to take the wedge product of those things. But so it turns out that you don't actually really need to figure out what those loops Ai and Bi are, because we're looking in this second quotient in the lower central series, which means that at some point we're taking the quotient by this huge subgroup of a fundamental group. And so we don't actually need the information of how to write this as a product of commutators, because most of that information is going to disappear when you take this quotient. So it turns out the only information that you really need to understand this delta bar is if you fix one edge, Eij, and look for where it is in this word, and look for its inverse in this word, then what edges are in between those two edges. So that's the information that will tell us about the ordering of all the edges in this word, and that's all the information that's needed in order to figure out this delta bar. And so what we found out is that so if we choose a basis for this h1 of u, then this thing delta bar, which is going to be trivialized in the second quotient in the lower central series, this has an explicit formula, and the explicit formula comes up by taking wedge products of those things and just figuring out what their coefficients should be. And usually the coefficients should be 0, but every once in a while the coefficient will be 1 or -1. So let me just give you an example. So for n equals 5, the Eij's, they are a basis for h1 of u. And so the Eij's wedge Eij's, they're a basis for h1u, wedge h1u. And the thing that's going to get trivialized in this lower central series is going to be this particular element of this particular wedge product. So there's some fun combinatorics about this, which I don't really fully know how to interpret, which are that this corresponds to a graph. And the way the graph shows up is that there are n-1 squared choices of this element. And if you place them on levels indexed by the value of j minus I, then this term delta that we've computed involves, can be expressed in terms of the edges of that graph. And when do you get an edge between one of these basis elements and the other? So you get an edge if that coefficient, if that element in H1U wedge, H1U has a non-zero coefficient in delta. And so which edges are those that showed up? Like, is there any pattern in which of these things show up and which of these things don't show up? And what's the pattern? Let me just say it in this example before first. Notice that E11 got wedged with E22, E33, and E44 with a coefficient of 1. And so when this value, the difference between 1 and 1 is 0, and these differences are all 0. And so those are all going to show up in delta. And then these differences, this difference is 0 and this difference is 1, and those will show up with a negative sign. And so expressing that, you can express that in terms of a graph. So you get if you arrange the vertices of this basis for H1 of U on levels based on the value of j minus I, then the graph that you get to describe this thing delta is a complete graph k n minus 1 on each level, and then each vertex on level I is connected to n minus 2 vertices on level I plus 1. And so this ends up being a subgraph of the ring of cliques with n minus 1 cycles of length n minus 1 removed. Okay, so all right, so that was sort of a long calculation, and the question is, well, why were we really interested in that? And so I want to tell you about an open problem about rational points that sort of was motivating why we were looking at that wedge product. So here's the open problem about rational points. So here's the Fermat curve, and we have these cusps, and we know that the points where one of the coordinates is 0, that they're defined over the cyclotomic field. But one question that's not known is, are those all of the points defined over the cyclotomic field, or could there be more? And so this question was considered by Clausen and Zermias and Saul. And what they did is they looked at the Fremont curve of degree p being 5 or 7, and they have a complete description of all the points on that Fremont curve defined over a number field whose degree is less than or equal to p minus 1. But already for p equals 11, there is not a complete description of the points of degree 10 on the Fermat curve. And so this was sort of one of the reasons that we were interested in looking at this problem. So what's the connection between Anderson's point of view and these rational points? Well, if you fix one of the points one of the rational points on the Fermat curve, and you embed the curve into its Jacobian using that point, then Anderson's result can be used to state the following: that if you fix an odd prime p and you let L be the splitting field of this field, and you look at the generalized Jacobian of this curve whose conductor is z, and you look at this particular Q rational point of that generalized Jacobian, and then look at the pth roots of that in the generalized Jacobian. And it turns out the number field generated by the pth roots of that point is this field L. It's exactly this field L. So I think I've already said everything on this slide, that this is the reason for trying to understand how this action of this absolute Galois group factors through this particular field L. So we have this explicit formula for how this action works on the relative homology with the coefficients in Z mod n. And the formula is too long to write down, but here's how it works out in some examples. So let's say you pick the prime 3, then this field L is generated over the cyclotomic field by a 9th root of unity and the cube root of 1 minus the cube root of unity. And the Galois group of L over K is then generated by 2 commuting elements of order 3. The first one, sigma, acts by multiplication by a 3rd root of unity on zeta 9. And the second one acts by multiplication by cube root of unity on this thing. So here's the group ring, Z mod 3 adjoin mu3 cross mu3. And so we would like to see how does this automorphism sigma act on the relative homology. And the way it acts on the relative homology is just by how it acts on that one chosen path that we started with. And the way it acts on that one chosen path is by multiplication by this explicit formula. And so here's the formula for B sigma minus 1. Here's the formula for B tau minus 1. And so here's the explicit action when P equals 5. In that case, the Galois group is generated by 3 elements that commute of order 5. And so these are how it's by multiplication by these things is how they act on the relative homology. So why were we interested in this second quotient in the lower central series? Well, it turns out there's a Kummer map. And what this Kummer map does is it takes a rational point of the curve as its input, and the output is a 1 cocycle. What does that 1 cocycle look like? It itself has an input, which is an element of the absolute Galois group, and the output is an element of the homology, H1 of x. And there's also an obstruction map. And the obstruction map starts here and goes here. So we have, so this is the thing that people are really interested in, trying to understand what are the rational points on the Fremont curve. And we could understand those by seeing what the Kummer map does to them and viewing those as 1 cocycles in this group. Then could look at the 1 cocycles and map them into this H2 of GK with coefficients in pi 2 mod pi 3. And what's known is that if you start with a rational point and first do the Kummer map and then do the obstruction map, you should get 0. That's what it sort of means for this to be an obstruction map, is that if you start with a rational point, this thing, you better not get an obstruction. So if we start with a rational point, then doing the composition of these 2 maps should be 0. And so how could this be done? How could this be used to understand rational points? Well, if we start with a 1 cocycle, we could see what happens to it under delta 2. And if it maps to something non-zero, then we know it doesn't come from a rational point. And so that's somehow understanding these 2 maps is sort of key for understanding this obstruction for rational points. So in order to actually compute these things, so that then has a lot of pieces. We need to understand the action of the absolute Galois group on H1 of x. That comes from Anderson's work in our explicit formulas. We also need to understand the action of the absolute Galois group on the second quotient in the lower central series. And that's what I told you about today. Less important, but is to understand how Heisenberg extensions affect that. It turns out that the Heisenberg extensions, using Heisenberg extensions, you can show that this space of cocycles is bigger than you might expect. And so you can find a subspace of this space determined by these Heisenberg extensions. And then there's this Kummer map, and we have the Kummer map on the points that we know. And so the last piece, so we've sort of gotten a lot of the pieces of this project put together, and the last piece is to understand how does this map delta 2 act on the span of certain cocycles in this space? And can we show that the image of that map is non-zero for a prime greater than or equal to 5? So let me just end by telling you a little bit about how this Kummer map works, because it's somehow less complicated than it initially looks. So the idea is that you pick a base point. So here's the base point 0, 1. And we think about the étale fundamental group. And what we want to do is start with a rational point and get out a cocycle. So let's call the rational point eta. It's a rational point. And we're going to take a path from the base point to eta in the curve x. For those of you who like these things, this is actually a fiber functor. So, and once we take this path, then if you have an element of the absolute Galois group, you can get a loop out of it by looking at the action of that element of the absolute Galois group on the path and then doing the inverse of the path. So let's draw a picture here. So if here's the base point, and here's eta, another rational point. And so we pick a path gamma from the base point to that point. And then since these points are both rational, sigma of gamma is another path from B to eta. And so if you then look at the composition of sigma of gamma and then gamma inverse, that then makes a loop. So what that means is for any element of the absolute Galois group, we get a loop, and then you can take the class of that loop in the fundamental group. So that's the Kummer map, which has input the rational points, and its output is 1 cocycles. And so this can be done explicitly for the rational points that we understand well. So let's, for instance, take this. Let's look at this one here. So let's look at this point, eta, which is zeta 0. So that's a point. That's our point eta on the Fermat curve, or zeta to the I 0. And we want to find what's the cocycle that represents, that's the image of the Kummer map for that point. Well, we know that that cocycle has to factor through the Galois group of L over K. So the only thing we need to figure out is how do the automorphisms in L over K, if you input one of those automorphisms, what's the output? And the output has to be an element of H1 of X. And it turns out the output can be explicitly described in terms of this, of the geometric automorphisms on the homology and the action of BQ, which is the action of this automorphism on the homology. So having explicit formulas for this action of the absolute Galois group and having explicit formulas for the action of these geometric automorphisms then allows us to completely describe the image of the Kummer map on these rational points. Okay, so I have a lot more slides here, but I feel like you all have been very patient with listening to me today. So I think I'm going to call it quits here, and just thanks for your attention.
Any questions for Rachel?
So when you started drawing pictures and mentioned the Fremont Curves, I was thinking you were going to say something with the words Pochhammer cycles.
What cycles?
Pochhammer, if you wish.
Oh, tell me about those. I don't know what those are.
No, I'm not going to be able to say much. So this reminded me that I think already Klein was using them to study some of the arithmetic questions, and maybe you're not going to be happy when I say related to hypergeometric functions.
Oh, yes.
There's work of Jürgen Wohlfahrt and maybe with Paula Cohen. They use some of this to look at certain Galois actions. I doubt that it goes in the direction you do, but vaguely recall.
Yeah. Oh, thanks. I'll look into that.
More questions?
So I couldn't help it as a amateur dynamicist, I couldn't
Yeah.
help but notice that 1 minus x to the p is an iterate, right?
Yeah.
It's like an iterated Galois loop. Level
Yeah.
2.
Mm-hmm.
And it's just a comment. I mean, does that, so the Galois group would be like a read product or something.
Mm-hmm.
Is that
Well, I mean,
integrated it 3 times? I mean, does that make any, is that interesting at all? Or?
yeah, I mean, one question you might ask is what happens if you look at the p squared coefficients rather than the p coefficients? And so it very well could be like a polynomial, that action might factor through a polynomial like that one. I wouldn't know how to prove that, but that there would be a possibility for that. Because one thing you'd like to do is, take these automorphisms acting on the coefficients mod p and sort of lift them to things that are acting on coefficients mod p squared. And so that action is going to factor through an extension of the field L. And so it's possible it could be something like that. Yeah. Yeah.
So this would be to start generalizing the result of Anderson? Are
Yeah.
there any results for anything other than the prime case?
Well, so Anderson's results are much weaker for when the number is not a prime. So I think that they give, the problem is that he has sort of a system of complexes, and he understands this action in terms of a map from one complex to another, and then other maps from these complexes. And so he gives a description of something in a completely different place. And what we did was to show that thing uniquely determines what you want when you have a prime. But if you don't have a prime, then this thing that Anderson computes does not uniquely determine this thing over here. There could be multiple elements that.
Cohomology class.
Yeah. Yeah. So I think I think that Ihara's work that is more p-adic, and so gives different information, but from a more p-adic point of view. But I think right now Anderson's work is not done for p squared. Yeah.
Any more questions?
Maybe I can add something.
No.
There's also that, so if you look at the homology of the Fermat Curve with mod n coefficients, that gives you the n torsion on the Jacobian. And so we only know that if you look at the points, the Cutfield points, the points at infinity on the Fermat Curve, so they generate some part of this n torsion. So if this is like this. So if you're looking at the Fermat Curve x to the n plus y to the n equals to n, and if you just look at the points at infinity, then they generate like 3n minus 7 dimensional subspace inside this n torsion. So if you knew sort of the rest where it comes from, then it becomes reasonable action.
All right, well, if there's no more questions, let's
Yeah.
thank Rachel.
This big glass of water.